All right, welcome everyone. We are going to start today's webinar on mastering the Opentrons Flex with the Python and HTTP API. Today, the speakers are myself. I'll be moderating this webinar, and we have Nick Deal, who is a field application scientist at Opentrons. He is someone that you'll be seeing going to your labs, developing Python protocols for you. And we also have John Clare. He's our solutions architect, the mad genius of Opentrons. He'll be going over the HTTP API section of the webinar. And today's webinar, we're really going to learn how we can use both the Python API and HTTP API to their full potential to control the Opentrons Flex.
All right, I think that's my key to jump in here. So thanks so much, Ethan. As Ethan mentioned, I'll be walking through the first half of this webinar, which is using the Python API on Opentrons robots, and namely highlighting some of the new features that have come about since the launch of the new Opentrons Flex robot. So let's talk about what a protocol means in the Opentrons ecosystem. A protocol for the Opentrons Flex or OT2 is a set of instructions written in code that gives the robot a step-by-step procedure to execute. And this can include liquid handling steps, so things like aspirations and dispenses with our pipettes, or non-liquid handling steps. And this could be things like comments or pauses, module action, or gripper action. And there are currently two main paths to create protocols on the OT2 or the Flex. This includes our protocol designer, which is an interface that will generate JSON files, or a Python API, which is going to generate .py files. And here's just a brief outline of some of the pros and cons of these two main creation methods. You'll see Protocol Designer's main benefit is that it's an intuitive drag and drop interface with no code for kind of basic protocols. For users that are not as comfortable writing code, they can still automate their protocols in the Opentrons robotics fleet. And our Python API really opens up the door to a lot of more high-touch control. You can use Opentrons modules more effectively. You can also use CSV imports and user-defined variables and conditional logic. And so we're not going to spend much time on Protocol Designer today, but I did just want to kind of give a brief disclaimer. This is the landing page for our Protocol Designer. It will be used for both Flex and OT2. And as I mentioned, it's a drag and drop interface, which requires no coding experience to generate to generate Opentrons protocols. So let's now dive into our Python API, which is the main subject of my part of this conversation. So firstly, what is an API? It stands for Application Programming Interface, and it's a type of interface in software that offers a service to lower level pieces of software, namely in our case, our hardware controllers and some other aspects of our system that allow you to run our robots. And this often allows the user to write code in a high-level programming language like Python to interact with lower-level code. So what's the Opentrons Python API? In Opentrons ecosystem terminology, our API is a simple Python framework designed to make writing automated biology lab protocols easy. They're accessible to anyone with basic Python and wet lab skills. It allows users to code automated protocols in a way that reads like a lab notebook. So we use language very intently to mirror what someone might be familiar with in the lab, things like aspirate, dispense, mix, transfer, things like that. And also it's open source and well documented as well. And what can our API do? So in short, it can automate any of your scientific workflows, NGS preps, nucleic acid extractions, dilutions, PCR, cherry picking. So we're kind of hard pressed to think of any application that we can't automate on our platform with a Python API. We can also do things like read and write to local files in the robot for saving some kind of data across runs. We can also integrate custom labware on the robot. So we're what we call labware agnostic. If there's a piece of labware that will fit on our deck, we can create definitions that will allow us to use that in our API. Here's a brief outline of what we'll go through today. So the main structure of our Python API protocols will be metadata and requirements, the run function, labware and modules, pipettes, and then finally commands. So let's jump in with metadata and requirements. Metadata refers to a dictionary of data that's going to be read by the robot server and returned to our client application. And the one required element of metadata is API level. Other elements that are shown in the image that I'll show you in a second are useful but not required. So they'll display some information like protocol title or a protocol description or the author of that protocol. Our requirements dictionary is needed for the Flex, and it's only recommended for the OT2. So if you're using the requirements dictionary, you'll actually want to move over the API level from the metadata down to the requirements. And here's a brief look at both metadata and requirements. On the left here, you see that API level is included, so this will likely be an OT2 protocol. And on the right, we have what it looks like in the requirements dictionary for both the Flex and the OT2. You'll notice that the main difference is the robot type will differ. On the Flex, we have the name Flex, on the OT2, OT2. So let's jump right into the run function at this point. The run function is kind of wrapping all of the functionality of our protocol. So everything that we want to do, any steps in our protocol will be contained in this run function. It must be named exactly run, and it takes one mandatory argument, which is the protocol context object. And so this object is kind of a global variable that will represent the robot and its capabilities. And its main responsibilities will be to represent, I mentioned that, represent the robot and its capabilities, and to expose the functions that make the robot execute actions. And let's get into that. So firstly, let's talk about our labware here. Labware refers to plates, reservoirs, tip racks, tube racks, any kind of plastics or static products that are used in liquid handling. And they will be laid out on our Opentrons robots decks. On the left here, you'll see a rendering of our Flex deck, and on the right, our OT2 deck, which you might be familiar with already. And the way that we let the robot know where our different labware is through a function called loading. And so we have our load labware function in the little screen grab on the top there. Here's an example of loading a Corning well plate into slot D2 on the Flex. And each labware is loaded onto a slot on the robot's deck. The deck is our liquid handling surface. And on the right there, you can see the different layout and coordinate system for OT2 versus the Flex. The load labware method is called on the protocol context that I've just mentioned, and it takes the following arguments: a load name that points to information about the physical dimensions of the labware so that the robot knows where each well is, a slot that points to the position on the deck. So in the Opentrons OT2, we'll have slots 1 to 11. On the Flex, we'll have a different coordinate system of A1 to D3, but the same idea here. And then lastly, we optionally can have a display name that will present to the user during the protocol run. And you might be wondering, where do I find labware that I'm allowed to use on the Opentrons platform? All of our labware, our standard labware, can be found on the labware library. And that's shown just a brief, the landing page on the right there. If your labware is not found here, you can create your own definition with our labware creator tool, which you can link to straight from the library. And it's best to have a technical drawing on hand for this to create the most accurate representation of your labware. And this will generate a JSON labware file that can be added directly to the Opentrons app for any protocol use. So now we've loaded our labware, and we now want to be able to access wells that comprise that labware. And we have a few different ways to do this. So the first way is by calling the .wells function on a labware object. This will return a one-dimensional list of all the wells that comprise that labware, which is shown on the top left image. You'll see that we're kind of iterating through each well in a column order. We can also return a two-dimensional list of rows and columns, which are shown on the top, the second two images there. And lastly, we can return a dictionary of all the wells or rows or columns keyed by their names. So if we call wells by name, we can index that dictionary or key that dictionary on the well name A1, H12, whatever it might be. And similarly with rows by name, we can index or key on the well name ABCD or the column name 1, 2, 3, 4, etc. We can also define and load liquids within the labware object in certain wells. And so we can define a liquid as shown on the left here. We can define a name, a description, and a display color, which takes in a standard hex code format for colors. On the right there, we can load the liquid into a specific well or set of wells, and we can name both the liquid definition, which we've shown on the left, and a volume to add to the well. And these liquids will be displayed during the protocol setup in the Opentrons app. Great, so now let's move towards modules. So modules refer to our hardware modules that exist in the protocols ecosystem. I'm sorry, in the Opentrons ecosystem. They load very similarly to labware. And so they'll physically connect to the OT2 or Flex via a USB connection, and they'll be loaded with an analogous function called load module. And it also takes in two required arguments, including a model, which points to the type of module specifically to load, and a slot to load the module into. On the right there, you'll see that we're loading a heater shaker module as an example, in this case, onto the protocol context object variable. And we're giving it a name. So the module name here is heater shaker module v1, and the location will be our slot. You'll note that our labware that we load on top of modules is actually loaded onto the module itself rather than onto the Opentrons protocol context. So let's talk about how we can kind of combine labware and modules in different ways so that we can use them together. We can leverage independent adapter and labware loads. So this enables us to move labware on or off of an adapter, namely with a gripper on the Opentrons Flex. And each labware has compatible adapters that will be allowed by the API. And there are a couple different ways to do this. So let's take a look at loading adapters and labware separately. The first line of code here is to first load the Opentrons heater shaker module with the load module command on the protocol context object, in this case in slot D1. Then the next step here is to load this new idea of an adapter object. And you'll see that we're calling a similar function called load adapter onto the module directly. And lastly, we can stack our heater shaker plate on top of the entire module and adapter assembly. And all we need in this case is the specific load name to load. We can also do this in one line, as shown on the bottom image there, next to together. So we can load a heater shaker plate by calling the heater shaker module.load labware. You'll see we have a load name, which refers to the plate, the location, and lastly, the adapter, which is the adapter name that we referred to above. So the modules are the peripherals that attach to the OT2. I'm just showing here the list, or I guess the collection of modules that we have available. You'll see going from left to right, we have a thermocycler module, which can mechanically engage and disengage the lid. We also have a heater shaker module with automatically closing and opening labware latch, a magnetic module, a temperature module, and lastly, a HEPA module, which sits on top of the OT2 and can actually be controlled through the API. So that one's a bit of an exception. Let's talk about some commands with our different modules here. On the left, you'll see our heater shaker commands. As I mentioned, you can close the labware latch to enable safe shaking of our labware and adapter assembly on top. You can set and wait for a temperature and a shake speed. You can also delay for an amount of time to shake at that set RPM, and then finally deactivate the shaker. You can also set a temperature, aspirate and dispense, and then lastly, wait for that temperature and delay an amount of time. So the top set there is called blocking commands, where we're waiting for a temperature or a shake speed by default. And the bottom shows non-blocking commands, in which we have to explicitly wait for a period of time before we continue with the protocol. Our magnetic module has two main properties, so we can engage or disengage the magnetic stage. I do just want to call out that the magnetic module is only compatible with the OT2. We have a new model of a magnetic block on the Opentrons Flex robot. We also have our temperature module command, so we can set a temperature, we can view a status, we can deactivate the module as well. Next, we have our thermocycler commands. So these are a bit more nuanced. We can set the lid and block temperature independently. The lid can ramp anywhere from 37 to 109 degrees Celsius, and the block can ramp from 4 to 96 degrees Celsius. We can also set a hold time in minutes and seconds to hold at that temperature before proceeding with the protocol. On the right here, we can see we can also set up a profile to run through a number of cycling steps for. So you'll see in this case, we have a 3-step profile with a set temperature and hold time for each of those steps. And we can execute a number of repetitions. So we can iterate through that list, in this case, 20 times. All right, so a great new feature of newer versions of our API is moving labware around the Opentrons robotic decks. And so we're enabled now to move labware around, off, or onto the deck without being tied to a specific slot. So the position is now a property of the labware itself. And we can specify moving labware manually or on the Opentrons Flex with a gripper. So manually, what this looks like is by default, we can call a move labware command from the labware object, wherever it might be on the deck, to a new location. Or we can do this automatically with use of a gripper. And you'll see here, it's the same structure, except in this case, we're calling that the gripper is true, meaning that the robot will activate its gripper to move the plate around the deck. So to or from a module that requires preparation, we need to actually be a little bit careful about how we think about moving labware. In this case, the heater shaker module we need to make sure that we're opening our labware latch before we move labware. So that's something you want to be mindful of. We can also have a special case on the right here, which illustrates moving to or from off deck. So you can think of a labware that you want to be aware of before you start your protocol, but it doesn't physically start on the Opentrons robot deck. And so in this case, you'll notice that we have a special constant called off deck that's called on the protocol API. So let's say our second tip rack in this case is loaded off the deck to start with. And then later on in the protocol, you'll see that we can move it from off deck to a new location, namely slot 1. You can also take a labware that's on the deck and move it off the deck as shown on the third to last line there. All right, moving now into our pipettes. Pipettes refer to the Opentrons fleet of electronic pipettes. You'll see that they're all structured similarly with a volume plunger and a tip ejector. Here's the kind of linear list of all of our pipettes. So on the left there, you'll see our Gen 1 and Gen 2 pipettes, which are compatible with the OT2. The right image is the list of our newer pipettes, which are compatible on our Opentrons Flex robot. We load them similarly to labware and modules. So we try to be as consistent as possible with our loading scheme. You'll see that we name a load instrument command, which takes in a model, which points to the range and type of the pipette, and a mount, so that would be the left or the right. And then finally, optionally, tip racks to tie to the pipettes that we know we can automatically iterate over that set of tips. On the right there, you'll just see all of our different load names that can be accommodated by our API for both the Flex and the OT2. And pipettes will perform the main liquid handling function of our protocols. So let's dig into some of our more basic commands here. You'll see, as far as atomic commands, we can load a tip rack and an instrument, in this case, a P300 multi-pipette, as we've just shown in the early part of this presentation. We can pick up a tip. We can set flow rates for aspiration and dispense independently, and that will be in microliters per second. We can mix at 10 repetitions, 200 microliters in this case, at a specific source well. We can aspirate a volume from that source well and dispense at a destination. You can also blow out that extra, you can think of it as the second stop of a manual pipette in a certain well. And lastly, we can drop a tip explicitly. We also have a list of complex commands which are comprised of atomic commands that we just ran through. And so our three main commands will be transfer, distribute, and consolidate. And that refers to one-to-one transfers, one-to-many transfers, and many-to-one transfers, respectively. We also have many keyword arguments that we can use to be really efficient in our coding. So we can let the robot know how often to pick up tips for each of these commands, whether or not to mix before or after, and that will take in a number of mixed repetitions and a mixed volume. You can say whether or not to touch the tip at the source or destination well. You can also provide an air gap or a blowout directly in those commands. So these complex commands allow us to be a bit more concise and a bit more efficient in our coding. We also have some high touch control that we can utilize here. So we can reference the specific positions within a well by calling offsets from positions within that well. So on the left here, you'll see that we can call the top of the well. That will refer to this top center of a well object. We can set an offset, in this case, 2 millimeters below the top of that well. Similarly, we can call the bottom of the well and move a 0.5 millimeter above that in this case. You can also move to the center. And we can move to those positions explicitly without handling liquid by calling a move to command on the pipette. On the right here, you'll see some non-liquid handling commands, which are quite frequent as well. And this includes things like comments, delays, and pauses. So a comment will just print out a message in the run log to the user. A delay will actually delay a set period of time before resuming. And finally, a pause will wait for user input before proceeding with the protocol. And with that, I'm going to hand it over to John to walk us through our HTTP API.
right, thanks, Nick. For everyone that has questions for Nick, we'll go over all of them at the end. But for now, I'm going to talk a little bit about the HTTP API. What is it? Why would you use it? How would you use it? So what is the HTTP API? So it's a little bit, it's another layer of control for the robot, along with the Python API. It is in some ways a little bit more technical, and it has a little bit different level of control. So HTTP, this is how you communicate with other things over a network. So if you want to control the robot from not inside of a protocol file that you've loaded, then you would use the HTTP API for that. The HTTP API is also how the Opentrons app communicates with the robot. So everything that the app can do is a capability of the HTTP API. So how's it different from the Python API? So while the Python API you can use to create protocols and liquid handling runs, the HTTP API is a way to either it can also create protocols and create runs, but it also can load pre-written protocols. So if you have a Python protocol or a JSON protocol created by protocol designer, you can use the HTTP API to load those and control your run. This is generally useful for people who want to control the robot from some third-party software. If you are happy writing your protocols using Python or using protocol designer and using the official app to upload them and run them, then you do not need to use the HTTP API. But if you want to use third-party software, this is the way to do it. Some benefits are it is programming language agnostic. You do not have to write any Python. You just have to be using any programming language that can create a network request. There are 3 ways I would identify that you could use the HTTP API. You can load a pre-written protocol, like I just mentioned. You can send atomic controls, atomic commands to the robot, or you can actually create a protocol using the HTTP API by adding a command one by one. Go to the next slide. So just to go a little bit more in depth to those things, uploading a protocol and control the run. This is the most common way that the HTTP API is used. This is the situation where you have some third-party software that you want to use to control the robot in the same way that the official application does. And the workflow there is you will upload your protocol to the robot using the HTTP API. I will have some code examples of how to do this after. It's a 3-step workflow. You upload the protocol, you then are given back. So to take one quick step back for people who aren't familiar with HTTP requests, the way they work, the communication works is it's a request response protocol. So you will send an HTTP request to the robot and it will send a response to you. So the 3-step workflow is to upload a protocol, sending a request with the protocol attached, and you will get a response that has an ID that is now associated with that protocol. You can create a run with that ID through another endpoint, and then there will be more endpoints to control the run by either starting it, stopping it. I believe they're called play, pause, and stop. Also, if you upload a protocol file this way, you will launch the protocol analysis the same way if you upload a protocol into the app, it will run an analysis on it for errors. The second way to use the HTTP API is by sending atomic commands to the robot. So you can send it simple commands, like a homing command to home the gantry. You can turn the lights on and off, but you can also send liquid handling commands. So the same commands that you can input into a protocol that Nick just went over, you can send almost all of those commands over the HTTP API as well. And then the third way you can use it, which I'm not sure I've ever actually seen, but you can do this, is you can create a protocol dynamically using the HTTP API alone. All of the commands that you would input, like uploading or defining the labware and the pipettes and the modules, and then sending move, aspirate, dispense commands, can all be queued up one at a time using the HTTP API endpoints. And then you can use the same play, pause, stop commands to control the protocol afterwards. Let's go to the next slide. So the first one, this is the most important one. This is the one that most people will use. You want to upload a protocol file and then you want to run it. So here are our requests and response. For the requests, this is using what is called curl for anyone that's not familiar with it. This is a command line utility that lets you send HTTP requests from your command line on your computer. I will go over the structure of a request real quick for anyone who's not fully familiar with it. The curl-x is just part of curl. This is telling it to use this utility. So the first thing you'll see is post in all caps. There are several types of HTTP requests. I believe all of our endpoints use either get or post. Get essentially means that you are asking for information. These are just utilities. These are standard ways of formatting requests, and post means you're giving it a command to do something or you want to make a change to it. Then we have the URL, HTTP, and then the robot IP. The robot IP will be replaced with whatever the IP address of the robot you're trying to communicate with is. And then you'll see this :31950. That is the port on the robot that the API server is running on. So you will always put in your robot's IP address and then : and then this port 31950. And then the / is right before where it says protocols. That is the actual endpoint that you are hitting. So anything after that 31950 and the / is going to be the actual part of the HTTP API that you're going to interact with. So here, just have a couple of examples. This one is, the -h is your headers that you will be inputting in, and this one just needs the Opentrons version. Most of them require the Opentrons version. This is the version of the software that is on the robot, and you can get this by, you can get it straight from the robot, but the easiest way to get it is going to be through the official app. Load up the app, whatever version of the application you're using to control the robot, it will push that version of software to it, and then you can look it up there. In this case, -f is the file. This is the protocol file on your computer. This will be a pathway to the actual file on your computer. You can upload more than one as well. Oh, you can upload, this second example is with custom labware. You can also upload custom labware to the robot the same way that you would do it through the application that I believe Nick went over. And then once you do that, you'll send this HTTP request and you will get a response back from the robot. And it'll give you a bunch of information. The most important one is the ID at the top. So this ID that starts with D97, this is how we're going to identify the protocol that we just uploaded to be used later in a run. The other things of interest are going to be the analysis summaries. So like I mentioned that it'll run an analysis on your protocol. If you want to request the output of that analysis, you will use this ID down here with the appropriate endpoint. And we can go to the next slide. So once we have uploaded our protocol, now we want to start a run using that protocol. So the way to create a run is we use this /runs endpoint, and then it has two headers, and then this -d that we'll be using is for data. And this is the way that you want to structure your data when sending requests. And in this one, you can see where it says protocol ID, this $sign bracket syntax means that you will replace this with whatever the correct value is. So this protocol ID is the ID that we got from when we got back from when we created, from when we uploaded the protocol file. So this is the ID we got back. So you create the run using the protocol ID, and you will get a response back from that that has another ID. And this is the one that identifies this run. And that is the most important piece of information here. And we can move forward. Next slide. So we have uploaded a protocol. We have created a run using it, but now we actually want to run our protocol. So there are 3 actions. There's only one endpoint. So we have this actions endpoint. And you can see again, it takes in the robot IP address as always, and then the run ID that we got in the response from when we created the run will replace where it says run ID in the request. And then actions, and then for the action type in the data, there are 3 options. There's play, pause, and stop. That will start a run. It will pause it, play it, and stop is equivalent to canceling the run. So that is the full workflow for using the HTTP API for running an uploaded protocol or pre-written protocol. This is an ideal way to integrate with third-party software. You have some software you want to run the robot with. This is a great way to do it. And again, this is exactly how the official Opentrons app communicates with the robot to do the same things. All right, so atomic commands. So some simple commands that we can send to the robot. These do not have to be inside of a protocol. These can just be done. There is a longer list. These are just a couple of examples. So here we can home the robot. It's command type home, no parameters. This will home the gantry. You can do this without having to create a protocol or anything. Controlling the rail lights, another simple thing that you can do. You can see down in data here in params where it says on true. If you were to replace that true with the word false, it will turn the lights off. And as true, it'll turn them on. You will get a response that tells you whether it thinks the lights are on or off, but also you can see them. You can do some other things this way, like homing the pipettes and other sort of high-level robot control. But more interestingly, let's go to the next slide. We can send liquid handling commands. So just like you would like to do when you're writing a protocol, for example, if you're writing the Python protocol and you want to do things like define labware, define a module, tell it what pipettes you have, and then actually doing liquid handling, where we want to aspirate from well A1 and we want to dispense into well A2. We can do these things immediately. So you do have to create a run, same way that we did earlier, but you will do it without adding in a protocol ID. This will create a blank run and will give you control over the robot. You can then add a pipette. You can see these are formatted the same way. We have this wait until complete equals true clause that I would like you guys to remember. That is essentially when you get the response, this will wait for the action to complete and then send you a response to tell you whether it happened successfully. And we will interact with that a little bit later. But and then you can see in the data line, the command type load pipette. So this is to add a pipette, command type load pipette, and then the type of pipette, the pipette name, which mount. These is all the same information that you would need to use to do the same thing from the Python API. So then you could, the examples after this I've abbreviated to just see this data object because the rest is the same. So you can see to add a tip rack, the data object just looks a little bit differently. Command line is load labware instead of load pipette, like you would expect. Load name, locations, pretty much what you would expect. And then pick up tip from slot A1. You will, the important thing here is that when you upload or send a command that defines something, so we're telling it we have a pipette loaded. When you get a response back from here, and I should have added an example, but it'll look like the old ones, like the other ones that we've seen already. You'll get a response back and it will have an ID. It will have an ID of the pipette that we can use to refer to that pipette later. Same for if we add a tip rack, so that when we go down to actually try and use these things, we added a pipette, we added a tip rack, now we want to actually pick up a tip. You can see as part of this data object, we use the pipette ID. We'll use the ID that was returned when we added it. And same for the labware, which the tip rack is in this case. And we can go forward. So setup versus protocol commands. What I just described, if you were to follow those steps, it would immediately, it would receive the commands and immediately start doing the things that you asked it to do. So by default, commands sent using this /commands endpoint are defined as setup commands. And things like that semantically make sense for things like defining labware, defining the pipettes, everything basically before you start moving the robot around definitely makes sense to be defined as setup. And that is what tells it to execute these things immediately. But when you give it other commands, by default, it also defines them as setup. So again, like picking up a tip or aspirating or dispensing. So it will execute them immediately. But let's say you don't want to execute them immediately. You want to create a queue, essentially create a protocol before anything moves. You can do that by removing that wait until complete equals true parameter that I mentioned earlier at the end, and adding to the data line this intent :protocol clause. So by default, we're getting you don't have to add it, but by default, its intent is setup. But we want to replace that with intent protocol by adding it to the data line, and then it will queue it up essentially. Once you've queued up a bunch of commands, there is a /commands endpoint that will return a list of everything, of every command you've uploaded it in order. Basically a plan for the run or what'll happen when you tell it to run. And then once you are happy with your list of commands, you can control it the same way you would control an uploaded protocol by using the play, pause, stop endpoints. And then I have an example on the bottom here with intent protocol added into the data line. That's what it looks like if you want to add these commands to be stored for later. And that is a very brief overview of how you would use the HTTP API. Here are some resources that will go a lot more in depth for some of the information you would want to use this successfully. The API docs are great. They are automatically generated, so they'll always have all of the commands in there. They'll have the header and data structures that you will need to use to interact with any specific endpoint, because they are not all the same. And they'll give you the structure of the responses that you will get. The second resource, the control examples, is a short little guide that kind of goes over the 3 modes of operation that I just went over. All the examples I pulled straight from that guide. And it's a little bit more in depth and has more examples. So definitely go through that if it's something that you're interested in using. And then the last resource here is a Postman collection. For anyone who is familiar with Postman, this is a Postman collection. For anyone who's not, all the examples I've provided were using curl, which is, again, how to send HTTP commands from your command line. Postman is some software that allows you to collect and save HTTP requests to be used later or to share with other people. So it's just a way to organize HTTP requests for testing, essentially, that I find useful. It's not a complete collection of every endpoint, but it has many of the useful ones. All right. If anyone has any questions for either Nick or I, please drop them in the Q&A section on the bottom and we will answer them.
Yes, thank you, Nick and John. I always appreciate you guys talking about your experiences with both the Python and HTTP HTTP API. I know that HTTP API has been in the background for a bit now, so it's always interesting to be introducing it to customers. So we do have a few questions, and if anyone else has questions, please submit them in the Q&A section, and I'll be reading them off to John or Nick. So this first question is specifically for the Python API. So Nick, so you introduced the idea of requirements and talked a little bit about metadata in one of your slides. I was wondering if we could go over that again and then talk about if the metadata replaces the requirements section or the requirements replaces the metadata.
Yeah, that's a great question. So I think to hopefully drive the point home, the requirements dictionary was added for the addition of the flex. So basically, we needed a way to let the robot know what robot we're trying to run on. The requirements dictionary is not needed for the OT2, and so we can still stick the API level in the OT2 metadata. However, if you're using the flex, you do need to explicitly call a requirements dictionary, and the metadata dictionary is optional. So on the flex, the requirements dictionary will point to the robot type being the flex and the API level. And then in the metadata dictionary for the flex, you'll only have kind of superficial information like the protocol title, description, author, things that can be read by our client application, the Opentrons app, but aren't necessary. So hopefully that makes things a bit clearer.
Yeah. So basically, requirements are required, and then the metadata has the useful information that the app or another interface needs to understand what's going on in the protocol.
That's right.
Then John, so if I was a Python user, if I was a previous Python user for the OT2, and I wanted to start learning about the HTTP API, what are the best resources for that? Like where would I start?
For the HTTP API, definitely the resources that I included in that last slide, specifically the guide, the startup guide, and the API docs are going to be the most useful.
And then is the HTTP API strictly for the Flex, or are we going to be able to use it on the OT2 if you have the OT2?
It does work with the OT2 as well. They use the same API. Obviously, there will be some commands that don't work on the OT2, especially in related to the gripper.
And then how does the deck expansion set work with the new coordinates on the Flex?
Yeah, that's a great question. So that was one of the impetuses for moving to a more well-plate style set of coordinates. So instead of 1 to 11, we're allowing for additional slots on the right of the Flex deck. So it'll be quite seamless to integrate. You can think of the well-played format. If we have, in this, without expansion slots, we have 12 deck slots, right? So we'll have A1 to D3. Once we add the expansion slots, that will just occupy column 4, which would be A4 to D4. So you can refer to those that way.
And this one's mostly targeted towards you, John. So if I had like an external software, for example, like an automation schedule, how do I integrate that with the OT2 or the Flex?
Okay, so we the question is, how do we integrate with like a existing like scheduling software, essentially?
Yep. Yep.
Okay, so we don't have internally written drivers for scheduling software today. It's something that we're gonna look into developing in the short term, but you can develop your own using this HTTP API. You can one-to-one map commands from the scheduler to the endpoints of this HTTP API to, send the commands that you want to get sent. So it's going to depend from scheduler to scheduler exactly how that's done, but it's definitely possible, and the HTTP API is the way that you would want to do that.
And then beyond schedulers, do we have any examples of drivers that we've already developed?
For the HTTP API, no. Those drivers would be whatever software is trying to control it, would have the drivers uploaded, since we don't control, that the third-party software is not our software. I don't have specific examples.
And then I think this is for the Python API. What's the convention that we're going to be using for the 96 head when we call it in a protocol?
Yeah, great question. So the pipette line for the Flex is actually completely independent from that of the OT2. So OT2 pipettes won't be compatible physically or in the API with the Flex, and vice versa. You can see behind me, we have the new Flex pipettes here, and this will follow a new convention. So I'll link to these in the resources that are sent out to all the attendees, but we're going to use Flex underscore the number of channels underscore volume range. So similar process, but slightly different naming convention. And
then if I had like a data set, say like in a CSV or something, if I wanted to interact with it using the Python API, how would I do that?
Yeah, absolutely. So CSV interaction is something that's really common in the Python API. It's one of the main reasons people tend to use it versus protocol designer. So a pretty common thing will be to consult the protocol library or have a protocol developed for you by my team. And basically, we provide an interface for you to select your CSV file for input. The Python file will parse the content of that CSV and basically generate a Python protocol that will represent your intended CSV functionality. If you'd like to do that on your own through coding the Python API, you can totally do that as well. There's a great package called CSV in Python that enables an interface for dealing with CSV data. Or you can always just copy and paste a string and parse it that way. So long story short, definitely is compatible through the Python API.
And we have examples of those, or how to use CSV files in our support documents and as well as our API documents, right, Nick?
Absolutely. There's also tons of CSV style protocols on the protocol library that I can point to for things like cherry picking, normalization, and a lot of other applications.
All right, we have a few more questions. Let me read through them. So can you stack plates on the Flex? So put one plate on top of each other, either on the deck itself or on the expansion slot.
Yeah, that's a great question. So currently, with the launch of the Flex, we're going to enable adapter stacking. So adapters will be things like aluminum blocks and similar style products that we don't tend to pipette to directly when they're by themselves. However, the intention is to shortly thereafter be able to support stacking labware by themselves, and that will include the expansion slots. So at launch, we won't be able to stack labware alone. We'll be able to stack labware on top of adapters and modules. Shortly thereafter, we will provide the ability to stack labware on top of each other.
Awesome. So those are all the questions. I'll give another 1 or 2 minutes for some additional questions to roll in. So our GitHub does contain a lot of our source code. Are there other resources in our GitHub that someone could use to explore the Python API or the HTTP API? Are there example protocols that someone could like work through and run it on their own machine to kind of learn the ins and outs of each API?
Yeah, so I can maybe start with the Python focus. Definitely is the answer. All of our protocols that are published online are fully available for our users. So we have nearly 1,000 protocols currently in our library. I will definitely send out the link to the library, which builds directly from a GitHub repository if you prefer a GitHub interface for searching around and dealing with protocols. For more advanced functionality, we also have something called the cookbook in our GitHub repository, which is kind of, again, higher touch functionality for more advanced Python users that you're welcome to take a look through. And I'd also like to flag that our new protocol library will be revamped and coming out in the near future. So stay tuned for that.
And I really always enjoy seeing what you can do with the robots, Nick. So do you have any like recent protocols you developed that you're really excited about?
Yeah, absolutely. I'll be sure to link to some useful ones. There's also kind of more getting started focused protocols that might be useful for someone who's getting acquainted with the Python API that I can link to as well.
And then John, how about for you? Are there like example protocols in our GitHub or in our docs?
There are example workflows in the second resource that I posted. A guide of how to do a few different things. It'll definitely, at least through atomic commands, get you through identifying or defining some labware and some pipettes and using them and interacting with them. And then there's also a guide in there on how to go through the full workflow of uploading a protocol that's pre-written and then controlling that run. Also, always the best example, the gold standard for how to use the HTTP API is actually the official Opentrons app. It communicates with the robot almost entirely using the HTTP API.
And I know you're always like working on some crazy stuff. So do you have any recent workings with the HTTP API that you're particularly excited about?
I think the most recent one that we have started looking into, although I don't have anything ready, is like the like that user had just mentioned, is around the green button go scheduling software. We're looking to get fully integrated with that. So I don't have a date that I can give you that will be finished, but it's something that we're actively working on. Cool. And that will be very exciting.
Awesome. So more to come, and check back on our GitHub or the resources that you linked in the presentation. We have one last question, and then we'll kind of close it out after this. So as you're developing protocols, Nick or John, what's the best way to simulate the protocols or like debug them in your experience?
Yeah, that's a great question. So we do offer a simulation tool which comes with our Opentrons Python package. So if you're familiar with installing Python packages, usually through pip, you can always install the Opentrons Python package. There's a command called Opentrons simulate, which will allow you to view the output of simulation of that protocol. Another way to do this is if you're next to a robot, go ahead and upload the protocol to the robot, go to setup, and you'll be able to see a step-by-step view with much lower lift on a technical perspective. All you need is the protocol and the Opentrons desktop app. So that's my recommendation. Also, on the just quickly to circle back to the question of documentation, I do want to just reemphasize that the best, I kind of gave the long and short of our API. The docs.opentrons.com is definitely the best way to learn about the Opentrons Python API. We spent a lot of time and a lot of effort developing that documentation to be as complete and thorough as possible. So please do check that out if you're interested in learning more.
Yes, the docs are an amazing place to go. I think there were just some updates to it, and it's looking fantastic these days. But I will conclude the webinar right there. A recording will be sent out to all attendees. Thank you again, Nick and John. Appreciate it.
Thanks a lot, everybody.
Thank you.